Okay, start again. Yeah, sorry. Thank you for patience. Yes, I must. Yes, I am talking after sampling before. So let's start again. Yes. So this is yes, outcome of study. Our aim is to mitigate unfair sampling in SLHD scheme. And we performed numerical simulations with different forward interaction strengths. As a result, we found that increasing the forward interaction makes the sampling fair. So, yes. Wait. Okay. From now on, I will discuss using more concrete results. In this presentation, we focus on homological bit and ferromagnetic item model. Yeah. Okay, this is the thing. We have calculated the probability of obtaining the ground states by changing the four-body interaction and quantum annealing time. This is the Hamiltonian for quantum annealing SLHD scheme. As with normal quantum annealing, there is a transverse field driver term and the problem term for the item model. And in addition, there is a term for the forward interaction. And this system has three degenerate ground states. We calculated each ground state probability. Okay. This graph shows the ground state probability. In this graph, the horizontal axis represents quantum annealing time, and the vertical axis represents the probability. The orange, red, and green lines represent the probability of obtaining each of the three ground states, and the blue line represents the total probability. If you look at the area on the right, where the quantum annealing time is long, you can see that the orange, red, and green lines are separated. According to these results, the ground state of the orange line appears frequently, and while the ground state of the green line does not appear very often. In this case, the sampling is unfair. Next, let us look at the behavior of another strength, yes, of forward interaction, stronger interaction. This graph shows the results with the forward interaction stronger than before. Please look at the right area. You can see that the degree of separation of three lines is smaller than when the forward interaction is small. At this time, the ground state probabilities of the three lines are more equal when the forward interaction is small. So you can see that the sampling is fairer than before. We can see that if the forward interaction is weak, sampling is unfair. But if it is strong, the sampling will be unfair. We have now seen that the stronger forward interaction makes the sampling fairer. But in order to compare how fair the sampling is, we will introduce a quantitative measure. Here we will use fairness and time to all solutions metric. First, let me explain about fairness. This is defined as the number of samples when the sampling can no longer be said to be fair sampling by chi-square test. But it is difficult to understand the definition immediately, so I will give an intuitive explanation of the very unfair case and not so unfair case. First, let us look at the very unfair case. Assume that we know that there are three degenerate ground states. In the very unfair sampling case, after you sample 5 times and you only get state A, and you will think this is not fair sampling. In such a case, fairness is 5. On the other hand, this is a not so unfair sampling case. In this case, states A, B, and C appears equally to a certain extent. However, after sampling 200 times, you will think this is not fair sampling. So this means fairness is 200. So this is the indicator of the degree of fair sampling. We have calculated fairness for the probability of the weak fourbody interaction. The horizontal axis is the quantum annealing time, and the vertical axis is the fairness. The graph for fairness shows a decreasing trend. This is consistent with our understanding that the probability graph shows unfair sampling for long annealing time. In the same way as with the graph of probability, we look at the behavior when the strength of the fourbody interaction is changed. We can see that in the adiabatic quantum annealing region, fairness also increases when the fourbody interaction is increased. This graph also shows that increasing the strength of the fourbody interaction leads to fair sampling. Yes, while fairness is a measure of the degree of fair sampling, but it does not include information on the ground state probability. So let us look at time to all solutions, TTAS, which includes information on the ground state probability. This is the estimated total quantum annealing time until all ground states are obtained at least once with a probability of 90%. As you may notice, TTAS is an extension of time to solution that can be used for multiple ground states. This is a graph for TTAS for several fourbody interaction strengths. We find that for short TTAS, it is important that not only fairness is large, but also the ground state is high. For example, please look at this part on the graph. TTAS is shorter when fourbody interaction strength is 3 than case of 10. We can see that when the fourbody interaction is 10, fairness is large, but the total ground state probability is small. So from these results, it can be seen that in order for the TTAS to be short, it is also important the ground state probability is high. And finally, fairness and the ground state probability are both important for fast fair sampling. And we want to know the optimal value of the fourbody interaction that balances fairness and the ground state probability. So as the last part of this presentation, we compare fairness under the same TTAS value and look for a setting of C that balances fairness and the ground state probability. This graph shows the relationship between the fourbody interaction strength and fairness. The TTAS is fixed for each line. In this graph, you may be able to see the trend of monotonic increase in fairness with respect to the fourbody interaction, but we think there is no clear rule. Although still now we don't know the exact rules of this, but we can see that the fourbody interaction can adjust the degree of fair sampling. Yes. We also perform numerical calculations for 5 logical bit systems with degeneration. In the 5-inch system, the trend of becoming fair when the forwarding interaction is increased is the same. But we are unable to find any laws of forwarding interactions that enable fair sampling. Our next step is developing a way to find the optimal forwarding interaction. Okay, I summarize this presentation and explain the future work. In the SAHG scheme, the forwarding interaction changes the degree of fair sampling. The strength of the forwarding interactions is an important parameter for fair sampling, and this is a parameter unique to SLG scheme. The best way to find forwarding interactions remains to be studied. We will aim to develop a way to find the forwarding interaction strengths for fair sampling as a future work. Yes, that's it for me. Thank you for your attention and thank you for your patience.
Good. We have time for a couple of questions for the speaker.
Thank you. Can you show again the figure where you showed the data for C equals 3 and 10?
Sure. Okay.
As a function of anneal time.
Okay. Sure.
So I would expect that the lines, orange, green, and red,
yes,
eventually turn flat, meaning that you have reached the anneal limit. Because in some sense, if you were to take the data for C equals 10 and anneal, say, to 1,000, it potentially would look similar to for C equals 3, just with a longer anneal time.
Yes, yes. As we expected, in longer annealing time, the behavior of C equals 10 is same as C equals 3 as we expected, but now we don't think that this behavior is same because we calculated fairness and TTAS. The behavior of fairness of TTAS is different for these cases.
Yeah, but what if you would anneal to 10 to the 20?
10 to the 20.
All these lines eventually would be horizontal.
Yes, that's true. Yes, I didn't show in this presentation, but yes, for example, C equals 50 or so. Yes, more these orange, green, red line tends to horizontal line, and yes, probability is lower, and the longer annealing time is necessary.
Okay, well, thank you.
Yeah.
You can talk.
Yeah, great.
There's a question here. Thank you for presentation. So I'm wondering that. So you showed that the degeneracy introduced by this SLHZ scheme, but also we know that some original Hamiltonian. Yesterday, the Matsuda showed that so as a nature of the program, we also have the degeneracy.
Yes.
So how do you think that will also improve with your strategy, or that is completely another problem?
Yes. Our intention is yes. We think that yes. When we use SAHZ scheme, we will have. I think we have advantage of the fairness can be changed by adjusting fourbody interaction. So, and in our results, we think that the large fourbody interactions can mitigate the unfair sampling.
Unfair sampling or unfairness in the original problem, right?
Yes, original problem has unfairness, yes. So,
Okay. Thank you. Okay, well, I think in the interest of time, we should move on. So let's thank all the speakers from this afternoon's session once more.